On September 11th, 2001, the world watched two of the strongest skyscrapers ever built collapse into lower Manhattan. The images were almost impossible to understand. Each tower had survived the enormous impact of a passenger aircraft. Yet, less than 2 hours later, both buildings were gone. So, what actually caused them to collapse? Was it the impact? Was it the jet fuel? Did the steel melt? Or was there a hidden weakness inside the towers? The real answer is more complex and more important than any single explanation. The aircraft did not bring the towers down immediately. The fires alone did not act on undamaged buildings. The collapse happened because several protective systems were damaged at the same time, allowing heat, gravity, and structural failure to combine in a deadly sequence. To understand that sequence, we first need to look inside the Twin Towers. Each tower rose 110 stories above New York and used an unusual structural system for its time. At the center was a group of massive steel columns forming the building core. These columns carried a large part of the weight and surrounded the lifts, stairs, and services. Around the outside was a dense wall of closely spaced steel columns. These perimeter columns formed a stiff frame tube, helping the building resist wind while also carrying gravity loads. Between the core and the perimeter were lightweight steel floor trusses topped with concrete slabs. The floors did more than hold people and furniture. They tied the core to the exterior walls and helped the whole tower act as one connected structure. At the roof, a large steel hat truss connected the core and perimeter. When columns were damaged, these connected systems could redistribute some of their loads into neighboring columns. That is why the towers did not immediately fall when the aircraft struck. They were not fragile buildings. Their size, redundancy, perimeter tube, and hat truss allowed them to absorb extraordinary local damage and remain standing. But surviving the first impact was only the beginning. At 8:46 in the morning, American Airlines Flight 11 struck the North Tower between floors 93 and 99. At 9:03, United Airlines Flight 175 struck the South Tower between floors 77 and 85. These were Boeing 767 aircraft moving at high speed and carrying thousands of liters of fuel. The impacts cut through sections of the exterior walls, damaged floor systems, and severed or heavily damaged some core columns. Debris traveled deep into each building. In an instant, the surviving columns had to accept loads that had previously been carried by the damaged columns. The forces did not disappear. They found new paths through the remaining structure. For a time, that redistribution worked, but the aircraft also caused another form of damage that was less visible and ultimately critical. The impacts stripped fire-resistant insulation from steel columns and floor trusses across large areas. This insulation was designed to slow the rate at which steel heated during a fire. Without it, exposed steel could heat much faster. The aircraft therefore created three connected problems. Structural members were cut or damaged. Loads were pushed into fewer surviving members. And much of the surviving steel near the impact zones lost its thermal protection. Then the fires began. Jet fuel spread across several floors and ignited immediately. The initial fireballs burned some of that fuel outside the towers, but fuel that remained inside ignited office contents over a wide area. Desks, paper, carpets, partitions, plastics, and other materials then kept the fires burning. This distinction matters. Jet fuel started and spread the fires, but ordinary office materials helped sustain them. The National Institute of Standards and Technology estimated that some fire regions reached air temperatures of about 1,000 degrees Celsius. But the steel did not need to melt. Structural steel melts at a much higher temperature. Long before melting, however, it loses strength and stiffness. As steel becomes hotter, it becomes easier to bend, buckle, and deform under load. Think of a metal ruler. It does not have to turn into liquid before it becomes easier to bend. Heat changes how strongly it can resist force. Inside the towers, exposed floor trusses expanded, softened, and began to sag. Heated columns also lost capacity. The structure was now damaged, overloaded, and being weakened further by uncontrolled fire. This was the turning point. A common description says that the floors simply fell one after another like pancakes. That does not fully explain how the collapse began. The official investigation found that the heated floors sagged, while many of their connections remained engaged. As the floors sagged, they pulled inward on the perimeter columns. Those exterior columns were already carrying redistributed loads. Some were damaged by impact. Others had lost insulation and were being heated. Now they were also being bent inward. Columns are very strong when loads pass straight down through them. But when a slender column bends sideways, its ability to carry vertical weight can drop sharply. Video evidence showed sections of the exterior walls bowing inward before collapse began. In the north tower, floors on the south side sagged and pulled the heated south wall inward. Core columns had also weakened. Eventually, perimeter columns on the south face buckled. Nearby columns became overloaded, and the upper section began to tilt south. In the south tower, severe damage near the southeast part of the core combined with persistent fires on the east side. Floors pulled the east wall inward. The east wall buckled, and the upper section tilted towards the east and south. At that moment, the problem changed completely. Before collapse initiation, the structure was carrying mostly static weight. Once the upper section started moving downward, that weight became a dynamic impact. Imagine placing a heavy object gently on a floor. The floor may support it. Now drop the same object from a height. Its moving mass creates a much greater force when it hits. The same principle applied on a huge scale inside the towers. Once the failing impact zone could no longer support the floors above it, the upper block began to descend. The story below was not designed to arrest the falling mass of many stories moving together. Connections failed. Floors broke apart. Columns lost lateral support. The falling material added more mass to the descending debris, increasing the destructive force as the collapse moved downward. This is progressive collapse. A local failure spreads because the remaining structure cannot absorb or redirect the rapidly increasing loads. The exterior walls peeled away in large sections. The core lost the floor systems that had helped to brace its columns. Concrete slabs fragmented, contents were crushed, and air and debris were forced outwards. The towers did not fall because every column failed at exactly the same instant. They fell because failure across the impact and fire zone allowed the upper mass to move, after which the structure below could not stop its descent. Gravity completed a process that impact damage and fire had begun. The south tower was struck 17 minutes after the north tower, but it collapsed first. It stood for about 56 minutes after impact. The north tower stood for about 102 minutes. Why the difference? The south tower was hit lower, between floors 77 and 85. That left a larger and heavier section of building above the damaged area. Its core also suffered more severe damage, including damage near a heavily loaded corner column. Fire burned steadily on the east side, where insulation had been extensively stripped from the steel. The aircraft also struck the towers at different angles. The location of column damage, the distribution of fuel, the arrangement of office contents, and the movement of each fire were not the same. This is why collapse timing cannot be predicted from fire duration alone. The south tower had a more demanding combination. Greater weight remained above a lower impact zone, and persistent fire attack exposed structural members in the area that later failed. The north tower was hit higher and had less building mass above its impact zone. Its structural damage and fire development followed a different pattern, allowing it to remain standing longer. Both collapses followed the same broad mechanism, but the exact path to failure was different in each building. You may have heard that the twin towers were designed to survive an aircraft collision. During their design, the possibility of an accidental impact involving a Boeing 707 was considered. But the surviving records do not provide enough detail to verify the assumptions, method, speed, fuel condition, or fire scenario used in that assessment. That difference is crucial. A structural calculation might consider local damage from an aircraft traveling slowly while lost in fog. It does not automatically cover a high-speed deliberate impact, widespread loss of insulation, fuel dispersed over several floors, damaged stairs and water supplies, and large uncontrolled fires occurring together. The conditions on September 11th were far outside normal building design events. In fact, the towers demonstrated considerable impact resistance. They absorbed the initial collisions and remained standing long enough for thousands of people below the impact zones to escape. According to the official investigation, approximately 87% of the estimated 17,400 occupants in the two towers evacuated successfully. That does not reduce the scale of the tragedy. It shows that the structures did not simply fail on contact. Their final collapse resulted from the combination of impact damage, lost fire protection, multi-floor fires, heat-weakened steel, inward bowing columns, and progressive failure. Remove one of those links, and the result may have been different. National Institute of Standards and Technology spent years studying the collapses. More than 200 specialists contributed. Investigators reviewed thousands of documents, interviewed more than 1,000 people, analyzed 236 pieces of recovered steel, carried out laboratory testing, and created computer simulations of aircraft impact, fire development, heating, and structural response. Its conclusion was not that jet fuel melted the steel. It was not that aircraft impact alone destroyed the towers. And it was not that an ordinary office fire alone could have brought down an undamaged tower. The investigation concluded that the aircraft impacts damaged structural members and widely removed fire-resistant insulation. Multi-floor fires then heated the exposed steel. Floors sagged and pulled perimeter columns inward. Weakened columns buckled. Collapse began at the impact and fire zones, and the falling upper sections triggered progressive collapse below. The investigation reported no supporting evidence that explosives caused the towers to collapse. The visible sequence began at the impact and fire floors, where inward bowing and structural failure had developed. This video is about the Twin Towers. So, what really caused the World Trade Center towers to collapse? Not one isolated weakness, and not steel melting. The aircraft severed columns and damaged floors. The impacts removed insulation from surviving steel. Fuel ignited widespread fires. Heat weakened floors and columns. Sagging floors pulled the perimeter walls inward. Columns buckled. The upper sections began to descend. And once that movement started, the lower structure could not absorb the enormous dynamic load. It was a chain reaction of impact, fire, structural deformation, and gravity. Understanding the chain does not make the tragedy less painful, but it does show why engineering investigations matter. Every failure studied honestly can help make future buildings safer. If you want more clear explanations of the engineering behind famous buildings, subscribe to Engineering Behind Buildings. Understanding buildings from the inside out.